This is elementary statistics, practice test number 5 or module 5, which covers chapters 10, 11, and 12. We are looking at chapter 12, analysis of variance. Given the readability scores summarized in the following table and a significance level of alpha equals 0.05, use technology to test the claim that the three samples come from population with means that are not all the same. By the way, just so you see what happened here, there are 12 pieces here. That's what N is for each case. That's N for Clancy, Rowling, and Tolstoy. Then X bar. So for this crew, the X bar is this number. For Rowling is this number, and for Tolstoy is this number. And of course, the standard deviation. That's the table. One-way analysis of variance is used for test of hypothesis that three or more populations have means that are all equal. As in H0, mu1 equals mu2 equals mu3 by analyzing sample variances. One-way analysis of variance is used with data categorized with one factor or treatment. So there is one characteristic used to separate the sample data into the different categories. And we use the F distribution for that. The F test used to compare two variances can also be used to compare three or more means. The technique is called analysis of variance or ANOVA. For three groups, the F test can only show whether or not a difference exists among the three means, not where the difference lies. The ANOVA test is right-tailed because only large values of the test statistic cause us to reject equality of the population means. Other statistical tests, Shafee's test and Tukey test, are used to find where the difference exists. Although the t-test is commonly used to compare two means, it should not be used to compare three or more. In the F-test, two different estimates of the population variance are made. The first estimate is called the between group variance, and it involves finding the variance of the means. The second estimate, the within group variance, is made by computing the variance using all the data and is not affected by differences in the means. If there is no difference in the means, the between group variances will be approximately equal to the within group variance, and the F-test value will be close to 1. Do not reject the null hypothesis. However, when the means differs significantly, the between group variance will be much larger than the within group variance, and the F-test will be significantly greater than 1. Reject the null hypothesis. The following assumptions apply when using the F-test to compare three or more means. The population from which the sample were obtained must be normally or approximately normally distributed. The samples must be independent of each other. The population have the same variance, sigma squared or standard deviation sigma. The samples are simple random samples of quantitative data. The different samples are from populations that are categorized in only one way. So we are using analysis of variance when we have more than two populations, and we are interested in doing the test of hypothesis for equality of their means. It's extremely important to understand you cannot use the t-distribution because you can use t-distribution maximum for 2, and if it's for 3, you have to choose 2 from 3 and run a combination of 3, choose 2, which gives you 6 different ways of doing it, and it introduces a large type 1 error if you go with the t-test. That's why we don't. Okay, so same question. We are basically testing, and it is important to know that it can be done by hand. It is extremely rare to do it because the calculation is very involved and it takes a long time to do it. I have it in my PowerPoint. So here we go using technology. You can use TI calculator or Excel, either way is fine, or any other source such as StatCrunch, R-Value, SPSS, you name it. This is the Excel value that has been calculated. A couple of things before we move on, I want to explain about this table. I want to start with the degrees of freedom for between. You have how many groups? You have 1 and 2 and 3. So this is 3 minus 1. Then each one has degrees of freedom n minus 1. So this is 12 minus 1, 12 minus 1, 12 minus 1. Or you might say total 3 times 12, 36 minus 3, which gives you 33. And they add up to 35. So this is how the degrees of freedom is calculated. The first column is the sum of squares that have been calculated. The rest of them can come from these two. So if you divide the first one by number 2, you get this number, which is the mean square. If you divide this one by 33, you get this number. The ratio of these two numbers is the test statistic for F. And when you have the test statistic, you can figure out the critical value from the table and compare them, or you can come up with the p-value. So as long as you have these two columns, you can come up with the rest. So here's how we write that. Mu1 equals mu2 equals mu3. At least one mean is different from the others. It's a right tail test, and that's a claim. This is how you write it always. In this case, you may have mu sub 4, mu sub 5, and even more. So we're going to use the technology. We see the number here, 9.46949, and we write that as the test statistic. This is the critical value. Now, this critical value can come from the table. Degrees of freedom for the numerator is the categories minus 1, and degrees of freedom for the denominator is the total number of data minus the number of categories, as I explained it here. Either way, we can find the critical value. We can also look at the p-value. The p-value is clearly less than alpha of 0.05. And whether you go with the p-value or the critical value versus the test statistic. So take a look at test statistic is way into the rejection region. Both of them result in the same thing, which is rejecting H0. So when we reject H0, we go back to the very first step. Rejecting H0, that means we are okay with H1, and the claim becomes true. So first part is from all these calculations. Then the rest is up to us to make a decision. The claim becomes true. There is sufficient evidence to support the claim that the three population means are not all the same. We conclude that those books have readability levels that are not all the same. Now, this was using Excel. If we were to use TI, we would put the data in L1, L2, L3. Then we use ANOVA test L1, L2, L3. We run it, we get those, and take a look at what you really need for the interpretation, which is the p-value. Now, as you can see, E minus 4, that means what? Move the decimal to the left by 4 places, which gives you the same answer we had here, or we have other values that you can see. This is the test statistic. We have it here. Degrees of freedom is 2 here. We have it here. Sum of squares, we have it here. Mean squares, we have them here. And degrees of freedom is 33 for this next group within, also known as error group, sum, and then the mean square. So you get basically the same information. The thing that TI will not give you is the critical value of F. Everything else you can get from there. Here's the next example, number 2, popular 3 weights. Weights in kilograms of poplar trees were obtained from trees planted in a rich and moist region. The trees were given different treatments identified in the table. We want to use a zero point 0.05 significance level to test the claim that the four treatment categories give us the same mean weight. So we have no treatments, fertilizer, irrigation, both fertilizer and irrigation. So to do that, we run either Excel or TI calculator, and here's the result. And before even we go there, we write the very first step, which is H0, mu sub 1 equals mu sub 2 equals mu sub 3 equals mu sub 4. And that is the claim according to question, because we are checking to see if they have the same mean weight. At least one of them results in a different mean. At least one of the treatments has a population mean that is different from the others, and we take it to be right tail test. So let's do the reading from the given table. This number is 6.14127, and that is test statistic. This number is the critical value, or if we were to use the table, degrees of freedom of the numerator is 1, 2, 3, 4 minus 1 or 3. And degrees of freedom of the denominator, 1, 2, 3, 4, 5. That means 4 for this one. There are 4 of them, 4 times 4, 16. Or you can say 4 times 5, you have 20 pieces of data, minus 1, 2, 3, 4 categories. That gives you 16. However you look at it, and alpha is 0.05. Now use the table. So whether we use the table, so 3, 16, this is a table. Remember, for F distribution, first and foremost, you have to look for alpha of 0.05 before you use the table, because they have different tables for different alphas. So 3 and 16, put it together, and that's the same value we have here. They're slightly different because of the number of decimals used. So we have that, and now we can also look at the p-value here, which is clearly less than alpha of 0.05. Whether we look at the p-value or compare the test statistic versus the critical value, in both cases, we come to the same conclusion, which is reject H0, because test statistic is way into the rejection region. Reject H0. So let's go back. When we are rejecting H0, that means we are rejecting the claim. The claim becomes false. There is not sufficient evidence to support the claim that 4 population means are all the same. We conclude that the 4 treatments do not result in poplar trees with the same weight. So different treatments have a different effect. This was done in a rich and moist region. We're going to do the same thing, but this time in a sandy and dry region, and we want to run the test. So pretty much the same question, but different region, sandy and dry. So we run the test, and here's the table. And the very first step, H0 and H1 is the same. Mu sub 1 equals mu sub 2 equals mu sub 3 equals mu sub 4. That's the claim. At least one of them is different. From the table, here's the test statistic. The critical value, again, we can go with the table, or it's given right here, which obviously is the same as the previous page. The p-value, however, is different. It's way larger than alpha. And you can look at the p-value or compare the critical value to the test statistic. Look at the test statistic way into the non-rejection region. As far as the p-value is concerned, this is the area. Area to the right of this test statistic, which is this huge area, which is 0.76866, and fail to reject H0. Now, if you are not rejecting H0, that means you are not rejecting the claim, and the claim becomes true. So fail to reject H0, the claim is true, There is sufficient evidence to support the claim that four population means are all the same. We conclude that the four treatments do result in poplar trees with the same weight.